All right, so we have to keep going with this story. Uh, Dante is out sick today, so he can't carry the class for us. So I'm gonna need the rest of you to talk to me today. Uh, why is it important if you guys don't understand something that you raise your hand? Yeah,
So that we can understand it.
yeah, because that is at the root of everything, as far as I can tell, is that things need to make sense. It's okay if you don't understand something. That means somebody else probably doesn't understand it too. So please talk to me as we go through this. We're getting into a little bit of a technical space, for better or worse, because we are starting to deal with lights that are far away, and we're trying to make sense of them and put together a story, right? And all we have is little pinpricks of light in the sky. They're different colors, they're different brightnesses, and we're going to try to make an entire story of the universe out of that. So there's a lot of assumptions, there's a lot of calculating involved in that, and I'm going to try to hold your hand through it as best as possible. So where we're going to go from here, last week we sort of built out this stellar classification system. We finished up the sun and talking about fusion, and we need to start thinking about the galaxy, and in particular all the other stars. But in order to even come up with half of a map for that, we really got to understand our distance to those stars, which is where we're going to be turning with all of this next. Now, before I get into that, let's review the stellar classification system we talked about before. Really anything from last week that sticks out in your mind, I really want you guys to bring that back. So we'll get to the distance stuff. We needed to review stellar classification. And before we even do that, the same thing I always ask you guys, what is at the heart of this class in terms of the two ideas that we're comparing side by side, and perhaps forms the basis of an entire renaissance in astrophysics and cosmology, if not all of science? Somebody. Yeah, what's your name? Cecilia. A liquid or a gas? Yeah. Now, why does that matter? It's three reasons I've been beating you guys over the head with. Come on, guys. I'm gonna just start calling your names because I don't have Dante here to save me. So, yeah, Evan.
Well, of the majority of them, like our current theories and our current math is based off of a gas model, and if it is liquid, that would just cascade changes to answers that we've been basing things off of.
Yeah, the whole story that we're going to be telling about everything else in the galaxy, all of the other stars, what all these lights mean is very, very different. You're going to start seeing those two stories diverge. You guys should be paying attention to these stories as they diverge, because I'm asking you for, a huge part of your grade in this class is going to be doing a final project where you compare a liquid versus gaseous approach to one of these different paths that we're going to be talking about. Okay, so the whole of astrophysics and cosmology, the stories diverge very, very intensely, as we're going to start to see here in the next few weeks. Really, really, really soon. We need to still understand a few more technical things. What else? Besides astrophysics and cosmology, you might talk to somebody on the street and they'd say, I don't care about the stars. Why does it matter? So why else would it matter whether the stars are liquids or gases? Everybody in this class is going to have to answer this question by the end of the semester. Kevin.
Because it can tell us how the sun does its fusion.
That's the second good reason, right? So the first good reason is it rewrites astrophysics and cosmology. Okay, maybe you don't care. Fine. It does change the way that we approach this fusion technology, and fusion has, at the bare minimum, been given billions of dollars of research because people are really hopeful we'll figure out how to do what the stars do on Earth so we can stop burning stuff, which would be really cool. And there may be lots of other applications of fusion technology too, besides just energy. So that's really important too. If we keep going as we've been going, treating fusion as this gaseous plasma reactor, we might be barking up the wrong tree. So that's the second reason. What's the third reason? Write these down if you don't know. You can just read them off your paper when I ask you, because I'm going to have to just start calling people's names at some point. I will not let you leave this class without realizing these three pieces. What's the third reason? Who cares if all of astrophysics and cosmology is barking up the wrong tree? Why does it matter? Owen.
To know the truth.
Yeah. Well, truth is a funny, funny word, but how about so things make sense? How about things so things...
So just like saying that's just how it is because that's how it is.
Yeah, things don't have to make sense, right? I think that's maybe for me, that's maybe the most important reason that we bring all of our observations into a narrative, into a story, a theoretical space where all of the pieces make sense with each other, right? So since the beginning of this class, I've been trying to point to some things that don't make sense, right? When we look at the kind of light that we get off of heated liquids and solids in laboratories, it's a very particular fingerprint of light. Does anybody remember exactly what that fingerprint is? This thermal radiation we talk about it as? This black body radiation? What does it look like? Yeah.
It looks like what we get from the supposed gaseous model of the sun.
What does the actual light look like?
Full light spectrum.
A full continuous rainbow of color, right? That's what a rainbow is ultimately, right? The water is actually acting like a prism and showing you all the different wavelengths of light, the different colors that are inside of it, right? Problem is, of course, what happens when we take gases and heat them up in laboratories?
They don't have the full color spectrum.
That's right. Yeah, they have very, very individual frequencies of color. They go off very, very strict lines of color, individual wavelengths, right? So these are like some really weird tensions, right? And so, you know, the current approach has been to kind of treat the stars as exceptions to that. Well, we can't, of course we don't see that in laboratories, but, you know, stars are special, they're huge, they're, I don't know, magical and weird. They do it somehow, and we'll just cobble together a bunch of other processes that might be able to approximate it. Okay, so that's where the tension kind of starts at. And all of these things that you guys helped me list just now flow downstream of that. And the goal of science in general is to provide a means by which we can tell a consistent story about the world around us, right? Guys, if the world doesn't have to make sense, it's a really scary situation where any big baddie can do what they want with your minds. And that's a scary situation. All right, thoughts, questions about this overarching paradigm? Yeah.
I suppose I'm curious, and maybe this is what we're going to get into later, but stars form in generally like immense clouds of dust that condense and it could explode or whatever. I'm curious.
We will definitely get into that, yes.
I'm curious how that would then, a dense cloud of dust and gases and things, become liquid in that sense. Because it is a giant thing of, would it just be the pressure and gravity condensing them?
So everything in the standard story is pressure and gravity because that's the only processes that can act on a gas, essentially. So first of all, we will explore like every possible angle on that in due time. Because what we're looking at is two very different stories of the lives and deaths of stars, really. So in terms of, the closer you look at the standard story about gravitational collapse of gas clouds, the more unlikely it starts to look. And we'll look at some of these, but you know, maybe the best way to think about that is that almost none of the gaseous nebula that we look at are gravitationally bound. So they're all basically floating away like gas probably would. Like if you took a balloon up into space and popped it, you wouldn't expect that it would fall back into itself. So for a long time, the argument has been, well, if you had a big enough balloon, maybe it would. Problem is gases are collisional and they tend to really just elastically bounce off each other into infinity. Now, what are some other processes that could bring liquids together? How about, Evan, you ever just been out on a cold morning and you just breathe out into the air and you see a big cloud in front of you? You know what that is?
The water coming out.
But the water's coming out of you all the time, right? Why aren't there clouds in front of you right now? What is it that makes it optically opaque, the water, all of a sudden?
I've never thought about that.
It's cool. It's good to think about that. Owen, yeah.
It's because our bodies are so warm that when we're in a cold environment, the water vapor is visual.
Why is it visual though? It's a good question. I mean, it's at the heart of what we're talking about, actually.
It's warmer than the air that's entering.
It is. And then what happens though chemically? What's the transformation that occurs? Does anybody know? Dylan, yeah.
Freeze.
Close, close. It is a phase transition, but it's not to a solid. It's to a liquid, actually. Little droplets are made. That's actually called a condensation reaction. So when gaseous molecules, let's say the gaseous waters, get cold, they actually start to electrostatically stick to each other, right? And that forms little droplets, which are actually condensed matter, which is what the argument about this liquid versus gaseous star is. Are the stars droplets, or are the stars like balloons without balloons to hold them in somehow? That's really what the question is. And so it's quite easy to condense. It's quite easy to condense gases in cold places, especially when they have a lot of heat going into it from whatever reactions they may have come from previously. So yeah, you end up telling, this is kind of where the story starts to diverge. So, I think I will take some time after, we'll take a little bit of time to look at stellar building blocks. So what kind of stuff is out there? It might kind of surprise you to realize that space is far from empty, actually. So if you think about, we talked a little bit about the stellar wind, or the solar wind, as it's called in our solar system. Does anybody remember what that is, basically, in some sense? Just it's basically the same stuff our star's made out of, but it's flying away from the surface of the sun at a really high rate, right? And so, in the gaseous model, that's driven by this magnetic acceleration at the surface, and there may be something to that. In the liquid model, it's literally just like sublimation. So it's kind of like when something goes from, it's basically evaporation at the surface, right? And then there may be some magnetic acceleration and things like this as well. But all that stuff, where's it going? Where's all that stuff that's evaporating off the surface of the sun? Where's it ending up? Yeah.
On the surfaces of planets and moons and asteroids.
And outside of our solar system altogether, right? So there's a lot of that stuff. All the stars are just cooking their surfaces off, and it's just piling up in interstellar space. So there's a lot of just raw material out there. Yeah.
Given how vast interstellar space is and the size of our star in comparison, when it is letting off the solar wind, given the inverse square law, wouldn't it just keep expanding until it was practically nothing?
Yeah, well, except you have to factor in time, right? Even if you go with the standard narrative that the universe was born yesterday, a few billions of years ago, that's a long time for stars to be cooking off and to be piling stuff up. And then, you can add into that, we'll take a closer look at all the building blocks. There's a lot of dust too, right? So, obviously we have a lot of planets and asteroids around here. All the other solar systems appear to have a lot of that same stuff. Those things get broken up, they crash into each other. There's junk everywhere in space, right? There's a lot of little bits and pieces. Occasionally, it seems apparent that stars themselves blow up as well. So there's a lot of junk that's flung out into interstellar space. It's actually kind of extraordinary how much stuff is out there. We'll look at that in detail. Maybe early next week, maybe the end of this week. I want to go through it carefully though, because we do have a lot of stuff to start to build stars out of. So, okay, what else? That's a really good question. Condensation on a cold winter morning. Condensation as the formation of liquids from gases as a natural reaction. Right, as a natural dissipative cooling reaction. It's literally a relaxation. It's an energetically favorable reaction. Yeah.
If we're looking at that model, and I know you said we'll get into it later, but
yeah, keep going. Let's go.
What then would spark the fusion that causes a collapse into the droplet?
Well, so droplet formation and condensation reactions are just a very, very primitive relaxation reaction about atoms that are just kind of slowing down. They basically combine in a way that allows them to relax in their motion, right? So it's a very, very common primitive reaction that you can experience anywhere. Are you asking when that switches over into being a star as opposed to just a bunch of droplets and stuff? Yeah. I mean, that's a really interesting open-ended question. So the funny thing is, even in the standard approach to stellar ignition, that would be the term, like the ignition of the star, right? The standard approach, unfortunately, is mired by the fact that this is happening inside of these dense, dusty, nebular regions. We can't quite see inside of them, right? So the best we can see is the stars that are starting to blow away all of the junk around them. I think that really with either approach, liquid or gas, it's going to come down to how much stuff is there, right? So one of the things that I worry about, even if this whole liquid star revolution unfolds, is will we be able to bring that kind of pressure back to Earth? So the star, our star even, not even a particularly large star, is huge. It's got 99% of the matter in the solar system contained, right? So it dwarfs all the rest of the in terms of just the amount of atoms in one place. It's extraordinary. All those atoms presumably are under the tension and gravity of one another, right? So that's a lot of passive pressure, all those atoms pulling on each other. Each layer of the liquid sun, even if you find a way to contain this gaseous sun and you have a lid on it, that's a lot of stuff pulling on itself, on each other, right? So I don't know, I don't necessarily know how we're going to pull that off on Earth, to be honest with you, although it does seem like people much smarter than me are working on it. And there might be passive ways to extract pressure. Because remember, all of our power processes on Earth that we generate power for our stations, they are all harnessing these kind of passive gradients where there's some natural flow, and pressure is one of those, right? Where atoms are moving from here to there, they're tugging on each other. The star has a real advantage by being big. So to answer your question, you got to have a lot of stuff in one place, basically. Condensation can bring things together really close in a way that gases can't do, because there's chemistry now involved, right?
Would that then imply, if we're like comparing it directly to condensation, where we're breathing out your breath, which is carrying liquid, like reaches the colder gas around it and then condenses.
Mm-hmm.
I suppose I'm curious that like if the star, if whatever spark is causing an insane amount of material to condense into a star, space is absolutely colder around a star, but where's that heat coming from?
The heat that is lost to the condensation reactions? Is that the question?
Or the heat that starts it?
So
It's like our bodies are warm, but then expelling
warm gas, which meets cold gas and then condenses the former. It cools the heated gas from your mouth, right?
Yes.
And it cools it, so it stops moving as fast,
Yeah.
and then it's able to stick to one another. Yeah. If it's moving really fast, the water molecules just bounce off each other and it stays saturated in the air, right? So, this is, in some sense, for both approaches, it's a huge mystery in terms of what the protostar actually looks like. I think in some sense, a good model might be something like a Jupiter or a brown dwarf, though, because I tried on, I don't know if I've tried on this thought experiment with you guys in this course, but I think maybe I did last semester, but maybe I did here. But it's worth re-mentioning. So what's the difference between a brown dwarf and a star like ours, let's say? Yeah, Kevin.
A brown dwarf, get the name of it, but it fuses deuterium.
Deuterium, yeah, heavy hydrogen. Yep.
A proper star in the main sequence fuses hydrogen.
regular old light hydrogen, normal hydrogen. But what's the difference between the two materially? Like, what's really the difference? They're made out of the same stuff. What's the hinge points between the two?
Isn't deuterium? How do you say it again?
Deuterium.
Isn't deuterium like 2 hydrogen atoms?
Yep. Well, it's not. It has an extra neutron. Yeah.
Oh, extra neutron.
By accounting purposes. Well, let's not get into the material atomics of that exactly. But what does that mean though? Like, what is it? What is really? If I have just looking at them from the outside, forget about the atomics of it all. What's the difference between I have a star right here in one hand and I have a brown dwarf over here? What's the difference?
Brown dwarfs give off more infrared than.
But what's the difference like between the two objects?
Size, mass.
Size and mass, that's it. That's really it. They're made out of the same stuff, more or less. So the star is heavier, let's say. Let's say it has more mass. It has more atoms in it, right? So at some point, this is the really interesting thought experiment. At some point, the difference between a star that has enough atoms to fuse to generate the pressure for neutral hydrogen fusion, that's a single atom at some point. There is literally a threshold where there's not enough atoms or tension, gravitational tension, in this mass of atoms called the brown dwarf, let's say. It can't do it. Now you pile on one more atom, and all of a sudden it can. It has enough mass in one place to be able to do that process, right? So there's a really, really it's not arbitrary. You know, we can define it in terms like Kevin did, in terms of the ability to fuse this or that or the other thing. But at the end of the day, the amount of stuff in one place is really what determines whether you're a star that's ignited or if you're just a brown dwarf. And what's the difference between a brown dwarf and, say, a Jupiter-like planet? Same thing. Same thing. It's just how much stuff is crammed into one place, right? So, you know, I think that in terms of imagining protostars, it would not be at all controversial, and I think this coincides with the both approaches to stars, gaseous and liquid, that protostars and brown dwarfs can be thought of as very much as failed stars. You often see them referred to, maybe even in your textbook, as failed stars, right? There wasn't enough stuff there to get that fusion reaction going, right? So, droplets perhaps coalesce. You know, the nice thing about droplets is once you have droplets, you can actually start to think about gravity mattering, I think. Gases, you know, by definition, they bounce off each other. Droplets definitionally interact electrostatically, so they're chemically sticking together, right? You can, you know, you even see this on the space station with little droplets of water. When they bounce into each other, they make bigger drops of water, right? So we have a mechanism. We'll come back around to that. What other thoughts on this line? Thoughts about last week's stellar classification system. Let's review that thing a little bit. So I wanted to talk a little bit about, I want to make sure that you guys kind of followed these pieces of the puzzle. So we look up at these pinpricks of light in the sky, and we talked about things that we can know from looking at these guys, right? Temperature of the surface. We look at the color of the black body curve that we get off these stars. And we say that's the temperature of the star. Is it the temperature of the star?
Who knows?
It might, yeah, go ahead.
Is that another situation where we can like math it out, but we don't know for certain?
Yeah, it is, because all that we know is the temperature of the rays, right? And some of the energy, the kinetic energy at the surface may be going into the convection cells. It may be going into conduction of electromagnetic structures, right? So you might lose some heat into other processes besides the rays themselves. Remember, a perfect black body turns all of the heat into light. Stars are not perfect black bodies, okay? They're inefficient in some sense. They do act thermally in the same way as all condensed matter. When it's heated, it will give off light, but they're not perfect. So already our classification system is like on kind of shaky ground. It might be a reasonable approximation at a first order glance, a 30,000 foot view. Yeah, we see the color of something, we kind of know what temperature it is. It's probably sort of true. It's not the full story though. So we're already a little bit shaky. And by the way, I'm not trying to like instill any kind of apocalyptic doubt. I just want you guys to see how much work remains to be done. So what else? Chemical composition. We can see the lines in the atmosphere. Because remember, the stars do have, I've been saying since the beginning of this class, gas versus liquid stars. Even the liquid model for the stars has it having a gaseous atmosphere, right? The corona, the chromosphere is all these cloudy things, right? If you look at a picture of the sun, you can see different layers of it. And there is definitely a gaseous layer sitting on top, much like there is with our Earth, right? So we see the chemical composition in those individual gas lines. We can see what atoms are in the atmosphere. Luminosity, right? This is a big issue. Why is luminosity such a sketchy variable in our spectral classification? Or how about, yeah, go ahead, Izzy.
Like we don't know how far away stars.
Yeah. So luminosity means not how bright it looks to us. It means how bright it really is. How much light intensity is being given off really in watts per square meter, like an actual brightness at some standard, in some standard measuring frame, right? And like Izzy says, the problem is the bicycle versus the semi-truck on the country road, right? Is it a bicycle that's close by, or is it a semi-truck that's far away? That one is going to keep coming back to haunt us, right? Because what we're going to try to do is, especially to move outside of just stars and start talking about galaxies and things like that, we have to construct a distance map, right? How far away things are. Things get really shaky because we start to assume that we know the luminosity of these bodies. And if we're wrong about the luminosity of the bodies, in other words, if the apparent brightness is mistaken in any way, shape, or form for the true luminosity, we might have mistaken a semi-truck for a bicycle. So does anybody remember from last time where we get the luminosity for a lot of these bodies from? There was a very famous equation. I don't expect you to remember it, but there was a very famous relationship from Arthur Eddington. Does anybody remember this? It's okay. I have a slide of it. Okay. So, Eddington very reasonably proposed that depending on how much stuff is there, the mass of the star, it's going to be able to do more fusion. It's going to give off more light, right? Totally reasonable idea. And so he proposes this relationship. Now, does anybody remember how we would figure out the mass of a star just by looking at it? Come on. Yeah.
Compare it to other stars?
Yeah, and particularly the motion of other stars, right? So how it orbits them, right? So we talked about that last time. There's this very intricate way, I don't really care if you remember this, but there's a way of looking at the Doppler shift of the lines in the atmosphere of two different stars that are orbiting each other to actually recalculate the orbital motion of those two stars. Once you know the orbital motion, you can back calculate the size, the mass, let's say, the gravitational interaction of those two bodies. So we look out, we see that we understand the masses of these two bodies, and from that we can back calculate the true luminosity. Now, it turns out that most of the way that we come to understand the distance between us and that star, the reality of the situation is that we assume that we know the real luminosity from this relationship, and then what we do is we compare that to what we observe as the brightness And as the brightness is some fraction of the true luminosity, then we can calculate just from the inverse square, just from the distance relationship, the way that light intensity drops off with distance, we can calculate how far away the thing is. It's a very simple and elegant idea, but the problem that comes back to bite us has to do with whether we're actually grasping the true luminosity of that body or not, right? Now, assuming these things to be as simple as we hope they are, we put them on a plot that looks like this, which will just keep coming up over and over again. This is kind of the central life story of stars plot. That's where we're going to go from now. So, we basically plot these things based on this luminosity, or assumed luminosity from these orbital mechanics for the most part. Although it gets even worse because a lot of stars just get kind of binned in based on their color, right? Oh, it's blue, it must be hot. That means there's a lot of atoms. That means it must be really bright. That means it belongs here on the diagram, right? Now, there's a few exceptions though on this diagram, right? So almost everybody fits neatly on this story, where if you're really, really bright, then you're hot, right? You got a lot of atoms, you're burning hot, you're blue, right? So the temperature, the spectral class, these are blue stars down here, right? So you're really bright, you're really hot, right? That makes sense. Problem is there's some little guys that we can't quite make sense of, because what happens is when we actually do that mass calculation, we see something like this, right? There's a really, really bright star, and there's a really not bright star. They're both the same apparent temperature, let's say. They're both blue stars, except one of them is not very bright. And we already did the orbital mechanics, so we know that the mass of these two stars is about the same. They're sort of orbiting each other equally, right? So that's really weird. That really messes with everything, because it'd be really nice if all of the bright stars were really hot, right? Sorry, if all the hot stars were really bright, but some of the hot stars aren't that bright. What the heck does that mean, right? Likewise, there's another pocket of stars over here that are, which is a bit more expansive and spans a bit more of the gamut, where you have a bunch of really bright, cool stars, right? So pretty much since the beginning, when the stellar classification system was erected, and honestly, it's been about 100 years that all of this has been going on. These two pockets, these what we call white dwarf stars and these red giant stars, have always been the sort of missing links. They're the pieces of the story that are much more difficult to explain. You have to come up with a consistent story for how in the world you have something that is really, really hot, but not very bright. You also have to come up with a story for how you have stars that are really, really bright, but they're really cool, right? It's always been a really interesting problem. So we're gonna circle back on this problem, and it really comes down to explaining this thing, right? These white dwarfs are a very, very strange phenomenon. Now, obviously, you get two completely different stories depending on whether the stars are liquids or whether they're gases. Why would you have two different stories for something that's really, really hot and really, really dim if you had a gas versus a liquid? This is kind of a high-level question. Yeah, Kevin.
Does it have to do with how dense it is?
No. Well, it sort of does, yeah. So in a gaseous model, the only thing you can do to make something appear dim would be to shrink it, right? You make the radius really, really small. So it's really, really hot, but it's just very, very small in size. That is the only tool available to you with a gaseous model. Why is that? Or maybe we should ask, what else could dim your star? Even if it was really hot, what could dim it if it actually had condensed matter structure to it? Emmeline? Its structure, yeah. Was that what you were going to say?
I was going to say the presence of like Clouds of dust or planets that might interrupt the light hitting.
We'll come back to that one. That's interesting too with periodic variable stars and stuff. We'll play with that. But no, guys, the actual chemistry at the surface, the literal lattice configuration of the molecules matters in liquids and condensed matter in general, right? Remember, diamonds versus graphite, pencil lead, right? Very different looking stuff, very different optical properties, right? You heat up a diamond and you heat up graphite, that graphite's gonna be a lot brighter looking actually, right? The diamond is actually pretty close to optically transparent. You really won't see much if you heat it up, to be honest. That's interesting. The graphite's an almost perfect absorber. They're both made out of carbon atoms, pure carbon atoms. The only difference is the arrangement of those carbon atoms. That doesn't come into play with gases. Gases never have structure. There's no relationship amongst the subunits in a gas. So in a gas, the only thing you can do to make something dimmer is shrink it. In a liquid, to make something dimmer, all you gotta do is mess with how the atoms are arranged with respect to each other, the bonding between them, in other words, right? You can completely change the optical properties, right? So to get something really hot to be really dim in a liquid model, you really just have to change the arrangement of the subunits. You bond them a little bit differently. To do it with a gas, you have to shrink the thing. These are the only two possibilities, really. So we have two very different stories for all of these dwarf and giant systems as we move forward. But we're gonna have to circle back on that because we need to pick on this distance thing a little bit. Because the story that we tell with everything downstream comes around to how far away those things are. Now, needless to say, we'd love for there to be an objective measure of distance. Unfortunately, a lot of the distance measurements we come up with assume the luminosity of the bodies that we're looking at to be the true value. And that luminosity is often assumed by sticking it on the map, on that HR diagram that we just looked at, right? Because of the color of the star and so forth, right? We'll see. This will make more sense in a second. All right. We'll come back around to all of this again. Needless to say, the story that we tell, even about not only about the births of stars, but the deaths of stars, is very different, right? So the standard story, just to preview it with the deaths of stars, in a gaseous model, all of the stars die quite violently, right? So they basically exhaust their fusion supply in the core. They have these periodic coughs. They lose layers. They eventually undergo some sort of violent explosion called a nova. We'll go through all of this in detail. In a liquid model, the stars just kind of cool off, actually, right? And what's interesting is that if you plot, my friend Jeff actually made this plot, but if you add on to the spectral classes and you start adding non-luminous bodies to them, or ones that actually radiate just in the infrared, let's say, you can actually plot pretty much all of the other bodies in existence, all the solar system bodies, all of the orbital bodies on that same main sequence, which is a really interesting clue that there might be something continuous about all of these bodies. Yeah, Kevin.
What's the difference between black dwarfs and dead stars?
Where do we have black dwarfs? Okay, so black dwarfs are a funny category. So certain low mass stars, so we can circle back on this after we talk about the standard story of the deaths of stars. So, you know, most stars are thought, like I said, to go through these violent ends, right? This is the standard gaseous story of what happens to stars. Some of them aren't big enough for that. The ones that aren't big enough for that are thought to actually cool off, very much like the story we'd tell in the liquid model. They're thought to just cool off. So a black dwarf would be a star that didn't have the mass to undergo these violent reactions at the end of its life, and it just sort of cooled off into this little ember. Now, in the standard model, that should take trillions of years, right? And since the universe in the standard model, standard cosmology, doesn't have trillions of years to have cooled off, there shouldn't be any of those yet, right? In the liquid model, perhaps perhaps we're not worried about these birthdays for various reasons we'll get into at the end. And maybe there's a lot of them, actually. Maybe the Earth is one of them. Okay. Yeah.
So then what's Death Stars? Like, are they just like kind of the same? Then?
Well, as these bodies cool off, so there's two options, right? So we either read these bodies as being on a true continuum, right? The main sequence as being an actual continuum where stars move, they cool, they're born perhaps very hot at the far upper left and hot and bright. And then as the stars lose material, right? The solar winds are happening on all these stars, right? As they lose material, they cool, right? They're losing mass. They can't do as much fusion. They basically cool and cool and cool and cool and cool and cool. That's one approach. That's sort of the approach to the condensed matter version of stars. In the gaseous model, we tell a very different story that I want to make sure that I get to. But essentially, stars are leaving the main sequence in the gaseous model. They're going and spending time as white dwarfs, or they're going and spending time first as red giants, right? They're transitioning between these pockets as they die in these violent deaths, basically. So that's really that's kind of to preview the two very different stories we tell about the lives and deaths of stars. In the condensed matter version of stars, they just kind of cool off, right? Maybe they cool off so much that they start to look a lot like other bodies that are non-luminous in the solar system around us, right? Maybe they end very much like they started. In the gaseous model, they go through these kind of violent transitions, right? And we end up with these ultra-compact objects, like these white dwarfs and neutron stars and black holes and things like this, right? Because the only way to make something dim with a gas is to shrink it. And gases are indefinite. I mean, ideal gases upon which all of these astronomical laws are built are indefinitely compressible. You can squish them forever and ever and ever, technically, according to these equations, right? Of course, the reality of a situation, which is the irony is somewhat lost on a lot of people, is that what happens in reality when you squish gases?
They become liquid.
Yeah, they become liquids. Okay. Anyways, all right. So, I also did a really, really cool podcast with this lady, not even to plug the podcast, but just to point out that there's a woman, an astronomer, who cataloged hundreds of stars that had blinked out of existence across the years between the post-war years in the 1950s to the 1980s. So she examined these Department of Defense satellite pictures. Actually, I think they were telescope pictures of the night sky, and just found thousands of luminous points in the sky that had gone completely black. That's in contrast to the standard model that says basically all the stars should be exploding. But what's the reality of this? How many stars have we seen explode in the course of human history alone?
0?
Let's say one, because I remember something.
Very, 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 very few. Yeah. You could count them on one hand. There's been several proposals. Of course, human history is sketchy too, right? People talk about some light appearing in the sky, dissipating. There's a few of those, but very, 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 very few, right? So where are all the dying stars at? That's a really good question, right? Okay, so we'll come back to that, guys, because we're gonna look at the birth and death very, very, very closely. Let's talk a little bit about distance, though, first, because I want to impress upon you that there's a lot of assumptions built into this classification system. So, I'm kind of working off of the idea that I'm going to go ahead and assume that this is a reasonable map of the phenomenon. I tried to tell you guys, temperature, maybe not the real temperature. There might be problems with that. Luminosity, it should sort of approximate mass, but we know it doesn't come with mass because we have white dwarfs and we have red giants. So it's not exactly a great way to figure that stuff out. So if we're going off temperature to put things on this diagram, along with some spectral information, there might be problems with this chart to begin with, but let's just assume that it's correct, right? Because otherwise we can't even start to tell a story. but it's certainly got some open-ended questions in it. All right, so let's figure out how far away things really are. This turns out to be easier with our local stars around us than it is with things that are super far away, which we'll see in a second. All right, what the heck is space? We haven't even talked about that yet. This is kind of funny. Yeah.
The area between stars?
I like that. Let's go with distance between. How about just distance between anything?
Sure.
In physics, space is really just the distance between things that exist, right? So actual physical bodies. Okay, so that's really cool. So technically, physically speaking, you can't ever be in space, right? Because it's not necessarily a substance that you can be immersed in. It's really just distance between things that exist. So that's one point to think about, because we're going to see the abuse of that word pile up very soon when we get to relativity and stuff like that. All right, so people have been able to calculate that. So space is defined as the distance between two points, really, two bodies, let's say, physically. What the heck is distance, right? What's distance? That's a good question. Yeah.
I was about to say empty space, but that doesn't help.
Yeah, I mean, it's really a system of measurement, right? For coming up with the dimensions, the length of bodies, and then using that as a system for measuring the separation between the bodies, right? Now, have you guys ever seen this chart before? It's kind of interesting because this is, maybe one of the oldest and still most relevant pieces of mathematics that you'll ever encounter, actually. So most of everything we're going to be talking about, and most of the work on determining distances on Earth, has been done using this idea. Does anybody know what this is? Huh? Yeah, that's right. Say it again. Sorry, I cut you off. I got too excited.
I said, oh, I'm right.
Yeah, the Pythagorean theorem, right? So, now, where did this come from? Anybody know? Yeah. Well, he's the famous. So Pythagoras is actually a really kooky, interesting guy. He kind of ran this mathematical cult in ancient Greece. Lots of lore about this. It's very interesting. He ended up sort of angering the authorities, and they sort of ran him out of town. Very weird dude. Now, it turns out that the Pythagorean relationship, which is shown here, which is pretty easy to understand, the area, if you just make a triangle, a right triangle, and you just build squares out of the lengths of each side of that right triangle, the literal area of these two squares is equal to the area of the hypotenuse square. It's that simple. It's literally just a relationship that naturally emerges from squaring this triangle, right? So it turns out that almost every civilization realized this. The Indian civilization seems to have realized this arguably quite a ways before the Greeks did. The ancient Chinese realized this. It's a pretty self-evident relationship if you start playing with triangles and squares. I think that probably people, I have no idea who first realized this. I imagine they were maybe even weaving quilts or something, making patterns and realizing, oh my gosh, the same amount of fabric is needed for these two things. I have no idea, but it's a very old and useful idea. So, we're going to basically start to apply that to how we would measure the distance between things. I'm going to save this one. Have you guys heard the story of Eratosthenes and how he measured the Earth back in 200 BC or whatever it was? Anybody heard this story? You heard this story?
Yeah.
All right, tell us the story.
If I remember correctly, because it's been a couple of years, he pretty much, I believe it was in Egypt.
Yep.
Roughly around there. He set up. I can't remember if it was a bet or something, but
Probably.
caused him to want to prove that the Earth was a sphere. And so what he did is he made two obelisks in two different cities, as we see there, Alexandria and
Siren. Yep. I think it's Siren. Yeah.
as it says, they were placed 500 miles apart, and by measuring the difference of the shadows at the same exact time in the two different places, he was able to determine that there was a difference between them, and you know, proving that the sun is not it's not always directly above. It's at an angle.
All right.
I explained that poorly.
No, that was great, Kevin. All right, so basic idea is that this dude thought that, like you said, he thought the Earth was a round sphere, which is arguably a really old idea too. The ancient Indian word for the Earth is something like round dirt or something like that. So people had this intuition for a long time. But yeah, he basically, he set up this experiment where there's two towns separated on this hypothetical globe that was in question, perhaps. And, assuming that the star is so far away, our sun, is so far away that the rays coming in are essentially parallel to each other, right? It's so far away that these rays are basically coming in at the same angle. Then, I drew this kind of poorly, but let's assume there's no shadow here. It's hitting it basically head on this pillar, right? And there's a shadow that's cast over here, right? Of this length here, right? I mean, I lost my, here we go. So this is where it gets really crazy. He realized that this is a measurable angle here, right? Inside of where the shadow is cast, you can just measure this angle, right? This should go all the way back to the center of the Earth, right? The basic rules of triangles is if you put the two of the triangles together with parallel lines, the opposite interior angles are equal to each other. So this angle is equal to this angle, right? This is like basic 8th grade trigonometry stuff, right? And everybody probably learned that one. Opposite interior angles, parallel lines are equal. Yeah, he realized that too. And he realized that, hey, if I know this distance, then I'm basically making a scale model of that triangle with the whole Earth over here, which means that I can know the whole distance of this triangle here, which means that I can actually multiply this out based on this angle, how much of the Earth is actually here. I can figure out this distance, I can scale it out to 360 degrees, and I know the circumference of the whole planet all of a sudden. And what's crazy is he was kind of right, actually, it turns out. So it's difficult to evaluate how right he was about it because they obviously weren't measuring things in kilometers back then. But they did have a unit of measurement and they had measuring devices that allow us to convert between the stadia that they used and the miles and kilometers that we use today. And it looks like he was right, like within a matter of percentages, a few percent for the circumference of the Earth, which is freaking crazy. And it's all based on 8th grade trigonometry, right? Pythagorean theorem. Just basically doing that simple realization that you can compare these lengths of right triangles, you can come up with relationships of how they fit together, and you can find the distance of something enormous, right? So it would be really nice if we could do that with stars too. And it turns out we can do it with some stars. So, you guys ever see like surveyors out there? Anybody have a family member who's a surveyor or anything like this? You see them out there, right? And you're like, what the heck are those guys doing? They're basically doing the same thing, right? So what they'll do is they'll set up some known baseline. They're basically making a series of two right triangles here, right? They're calculating the angle to some distant point that they sight with their little surveying telescope thing or whatever it's called. They go down the baseline, some measured distance, and then calculate the same angle, how much they have to turn off the baseline to focus on that distant object, which I guess is a tree in this picture, right? Now all of a sudden they have that interior angle and they can back calculate just using the a squared plus b squared equals c squared business and the basic trigonometric relationships. All that stuff you guys had to learn in middle school, sine, cosine, tangent relationships, which are just literally relationships that originally just emerged in tables, right? So you guys use calculators to do that stuff. They originally just calculated with this angle, you will have this relationship between the different legs of the triangle, right? And they had these huge tables to do that. You can obviously use a calculator now. Anyways, the point is, just knowing the angle, the size of the baseline, you can calculate the distance, right? The long arm of that right triangle, whatever it's called, the long leg, you can calculate that. And so surveyors use this all the time to figure out how far away something is without actually having to, walk all of the steps out or whatever the heck they did prior to this. So that's pretty cool. Now, it would be really nice if we could do that for everything in the universe. What is the problem with that? What could get in our way? Yeah,
It's like other objects that we are seeing when we're coming in contact with that light. It's coming to us.
I'm more thinking like, what's the problem with doing this experiment? If that's a star and this is us at B, what's the problem here? Yeah.
Could it be that maybe we're not seeing an accurate picture as one star's light is being bent by another one? Gravity.
You're getting too technical. We'll deal with light bending eventually, though. Emmeline. Ethan?
No, would it be that we can't place A far away from B?
Yes, that's exactly right. Yeah. So if this is Earth over here at B, how do we get a big baseline, right? Because remember, if the star is sufficiently far away, the triangle is going to collapse, right? If it's really, really far away and my baseline's only over there and something is, 100,000 kilometers away, my angle for that when I move over here is almost nothing, right? So I need a huge baseline, right? The way around that is to have a huge baseline. So how do we get a big baseline on Earth? It's like, yeah.
Two separate points on opposite sides of the Earth.
Exactly. So, in fact, that's basically the biggest baseline we can even possibly get, right? I can't think of a bigger one, right? So basically, where the Earth is at any two poles of the year, so summer versus winter, spring versus fall, 6 months apart, we're about as far away from we've made A about as far as we possibly can from B, right? And so that's it. That's what we do for stars that are close enough for this to work. Now, this is really quite interesting because even with that enormous baseline, and even though there should, in theory, be a bunch of stars pretty close to us, relatively close, right? What's crazy is that the stars are so far away that for most of the history of science, going back, even to these ancient Greeks, and then leading all the way up almost into the 1800s, people couldn't see that. They still couldn't see any angle of separation, even in the spring versus the fall. The baseline was not big enough to resolve any real angle between the stars. What did this make them conclude? Yeah.
They're probably all fixed in place.
Yeah, it made them conclude that we were in the same place, that the Earth was at the center of the universe, actually, right? They said, oh, well, the Earth's, if the Earth was going around the sun, then there should be a nice parallax. By the way, I didn't introduce this word that the surveyors use. It's called parallax, right? They said there should be a lot of parallax between the 2 points in the orbit, right? They didn't realize that the stars were light years away. They had no idea how far the stars were from us, right? So they said, but there's no measurable angle of separation and in spring versus fall. we must be staying in the same place. We're not orbiting the sun. Now, parallax is, by the way, this word parallax, you guys heard this before?
In the
A little bit?
The
What's that?
textbook.
The textbook? So parallax is kind of cool. I mean, you can like, it's really important to you on an everyday basis, right? So why do you have two eyeballs?
For depth perception?
For depth perception, right? Distance perception, right? Because what your brain is doing when it's calculating is it's literally doing this exact same experiment that the surveys are doing. You have a fixed baseline, separation between your eyes, and what you're doing is looking at the angle of separation as those two images diverge at different points. Now you can try this out, right? If you put, you put your finger in front of your face, kind of close, and you close one eye and then close the other, you notice that the finger kind of moves, it kind of jumps from side to side, right? Now put the finger really far away as you can. Jumps less, right? The angle of separation is less, right? So this was the crisis for most of astronomical observation. That stars are so far away, the finger is so far away, and your baseline is so small and fixed, being confined to the orbit of our own solar system, that we couldn't really see much of a difference at each one of those points, right? This really required the advent of high magnification telescopes in the late 1800s before people were able to even start to catalog any parallax whatsoever. So that's pretty crazy. And the closest star to us, right? It should have the most parallax, right? The closest star to us has a parallax, the angle here is only 1.5 arc seconds. That means a single arc second is 1/3600th of a degree. So a circle has 360 degrees. An arc second has 1 out of 3,600 of those. And the angle that those guys had to measure with those high-powered telescopes in the late 1800s, they were finally able to do, was 1.5 out of 3,600th of a degree. It's a really, really, really tiny angle that they're measuring of parallax between the summer and the winter, or between the spring and the fall, right? That's how far away the other stars are from us, right? It's totally insane. Okay. Questions? Thoughts? Okay. So we actually can define distance. We start to be able to actually define distances in terms of this angle of separation. So it's actually easier for us to talk about the parallax that we see for a star. In some sense, for an astronomer, that's literally the readout of the telescopes is telling them the parallax angle. We actually convert that into a unit of distance at some point. So we define this new unit of distance called the parsec, right? And the parsec is basically how far a star has to be away to be 1 arc second away. So that's 1/3,600th of a degree of separation in the night sky, right? So that's a parsec. And a parsec can be converted into distances. It can be converted into light years. It's about 3 light years away. So there's no star even within a parsec of us here other than our own sun, right? So these are extraordinary distances, and even so, we seem to be quite alone in our neighborhood, which is really, really interesting. All right. So they've gotten better at this in modern times, and there has been quite a few stars whose distances have been logged according to satellite measurements. They basically take a satellite, they park it out at L2. Anybody know what L2 is? Talked about it maybe before. So L2 is just this nice little stable point where the pull of the Earth and the sun is kind of balanced out. So you can actually stash satellites out there and they'll just kind of follow the Earth really stably around in our orbit. There's a few of these, they call them Lagrange points, but there's L points, right? So park a satellite out there, and as the Earth moves around the solar system, it's taking these measurements of these angles, right? And it's doing it very, very, very precisely. And so, you know, something, well, let's see, at this point, this one was launched in 1989. They have thousands of these stars they have parallax for. And they can reach out, they can get pretty far, actually. So they've gotten out to, you know, a couple of hundred light years in terms of stars they can actually get with accuracy of maybe 10, 20% on this angle business, right? In terms of parsecs, so distance in parsecs. But guess what? A couple hundred light years isn't that great, right? It doesn't get us very deep into the cosmos. And so if we want to figure out how far away something beyond a couple hundred light years is, what do we do? All right, well, one clever thing that people came up with was the idea of standard candles. So, you know, just like our classic example with the semi-truck and the bicycle, if we had, let's say, you know, something very obvious like an iPhone flashlight, you know, on some particular make of iPhone, and we gave it to somebody and we sent them down to where that bicycle or semi-truck was, then we would know how bright that thing it was, right, to begin with, and we could compare it to the object that they're next to, right? And then we would know. So that would be a standard candle, right? The iPhone in that case would be a standard candle. So people went looking, is there anything that's standard that basically we know it's the same object that has a known brightness, that if we see it in different places, then we would know if it's dim, we know it's absolute brightness, and so we can back calculate the distance. The first hope for these was variable stars, actually. So what's a variable star? Well, it's an object, hopefully a star, who pulses, right? Its brightness changes with a rhythmic periodicity to it. And we'll talk a bit later about how the pulsating star fits into our model for the lives and deaths of stars. There's some really obvious pulsating stars, by the way. You guys, anybody ever seen Betelgeuse before?
Yeah.
Not the movie.
No.
You seen the actual star? All right, so you guys know the constellation Orion? It's probably the easiest one to see, honestly. If you know any constellation, Orion's those 3 stars in a row, right?
It's his shoulder, right?
It's his shoulder, yeah. I believe it's upper. I was going to say upper left.
Up our left,
Yeah.
his right shoulder.
Oh, his right shoulder, yeah, if he's facing you. Yeah, good point. Okay, there's you can see it very obviously. Actually, I wouldn't bet money right this second on whether it was the right or left shoulder, but I think it's the left. My point is, if you go out and look at Orion and you look up to, if that's Orion's belt that you're staring at, look up at his shoulder, you'll see a reddish yellow star that's pretty different looking from the rest of them. That thing actually changes on the order of days. So it'll be very bright one day and very dim a couple days later, right? That's probably the most obvious pulsating star that you can see. And the theories for why it's pulsating and for why all of these are pulsating is very different depending on the star. But there was one type of star that people really started to focus in on. And these were found in the Cepheid cluster, which is a local cluster of stars. And they seem to have there were several of these, they seem to have a very predictable rhythm to them. They would brighten and dim. And through parallax measurements, we could figure out basically how far away that Cepheid cluster was. So when people started seeing these same light curves, the dimming, the periodic, the time of the periodic brightening and dimming of other stars that weren't in that same nice nearby parallax region, they thought, okay, those are the same kind of stars. They're like these Cepheid variable stars. And they started to notice there's a few different types of these. There's also another group called the Lyrae, RR Lyrae pulsating stars. And so that allowed them to actually extend their distance measurements all the way out, because now if you know how much this standard candle's intensity is, then you can go and look at where that thing is out in regions beyond where you can actually get those parallax measurements. This worked pretty good to a point. So at some point, the problem actually proved out that there was not just one type of Cepheid star, actually. There was two types of Cepheids that were confused for one another. And so, you know, maybe a decade into doing this kind of distance mapping of stars using the Cepheid method, they realized that some of the stars were actually twice as far away as they thought that they were originally. So they had to completely redo the map based on these two different types of Cepheid stars. Now, this is kind of interesting because there had been a debate unfolding that wasn't really settled until about 100 years ago, which was, are there other galaxies out there? Now, that seems pretty crazy because today we know there's trillions of galaxies, actually. In fact, a lot of what you probably think are stars in the sky are other galaxies when you zoom in on them, right? But since you couldn't actually see individual stars out there in those galaxies, people thought they were just kind of little swirling nebula, little, you know, gassy or dusty motes just kind of swirling around. So this matter wasn't actually settled until really these Cepheids became understood as a reliable means of noticing pulsating stars. And some of the local clusters that were outside of our galaxy were given distance assignments that made them outside. There was basically stars in these little tiny galaxies. So we start to look at our galaxy a little bit more. We're going to see that there's actually these little, I don't want to call them like baby galaxies kind of clustered around ours, right? It's not maybe not the right word, but there's little clusters of stars that are kind of right above our disk, right? They're not part of our galaxy necessarily inside of the same disk, they're outside of it. And people began to actually recognize that, oh my goodness, I think that we're inside of one of those swirling little thingies that we can see in our telescopes. Those are actually entire galaxies. And that is the point where people needed a new standard candle, because you can't see individual galaxies and those other swirling things. They just look like little swirls on the telescope. And so you needed another standard candle to make sense of this with. So this is where things start to get really, really bizarre and really, really sketchy, because again, the only direct measurement of distance we can do is this really nice, in so much as you even consider it direct, is this trigonometric parallax stuff, right? It's pretty reliable. Surveyors use it. I would bet on it. The Cepheids fooled us once, right? We were wrong about the distance between Cepheids because we confused two types of pulsating stars for each other, and we had to redo our entire catalog of stellar measurements based on these all of a sudden one day. When it comes to distances that are so far away that we can't even see the individual stars, we're really facing a whole new challenge, and that's going to concern the light curves of supernovae, so explosions in other galaxies that we see. Now, how many explosions have we seen of these stars exploding? We kind of talked about this at the beginning of class a little bit. Not many in our own galaxy, anyways. We've seen very, very few, and so our understanding of them is equally, let's say, unrefined in some sense. And so we're projecting our very, very sparse experience with them in our galaxy onto other galaxies all of a sudden, when we start to move out to other galaxies and trying to estimate how far away they are, because we're comparing flashes we see in other galaxies that are trillions of light years away. That's not fair. They're not trillions of light years. They're trillions of miles away. They're really, 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 really far away. And we're trying to map those onto extremely infrequent and hypothetical events that we don't really understand the distance to in our own galaxy. So that's where we're headed to from here. And as much as we can map our local galaxy using these Cepheids, and maybe even the little clustery, dwarfy galaxies that are kind of hovering above our galaxy, we have to make some huge leaps of faith to get outside of our own galaxy. And so that's where we're going to turn to next, is that in some sense, the story that we've told, this is just another look at the where these variable stars fit onto that big diagram. This diagram, I cast a little bit of doubt on the reliability of it at the beginning of class. Don't totally know if the temperatures are right. Luminosities are a little bit sketchy. They're kind of circularly referenced, which is also a dangerous thing to do. But what's worse is that this is quite as unreliable as I've kind of painted it to be. It's most reliable with the stars around us, right? Where we actually can get distances, like real direct-ish distance measurements to them. Because if we know the real distance, then we can say that the brightness can be scaled and give us the real luminosity of the star, right? When we start making these kind of abstract leaps to how far away something is and then trying to pin the luminosity on it, it gets even more difficult. Yeah.
Giants.
Oh, we'll get there. We'll get there. Where does it say that? Oh, hypergiants. I've never even heard that word. That's funny. Yeah, we'll get to those. We'll get to all of these giants. Yeah. So, I mean, the answer is there's a story. There's a story from the textbook we can tell about these different giant and dwarf stars, but there's problems with that story. So the answer is that a lot of that story has to be written still, probably. All right, so yeah, we'll pick up with the lives and deaths of stars on Thursday. Have a good week, guys.